Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is filling bookshelves. So you are given an array books where each entry in this books array gives the thickness and the height of the books containing that are represented by this array. And so the first entry indicates the thickness and the second one represents the height of the book. Okay, and you are also given another variable or another integer which is self width. So you want to place these books onto a bookshelves, and you have to total that have a total width of self width. Okay, so the situation is like this, that let's take a fresh slide. So you are given some bookshelves, okay, like this, and these all bookshelves are having a fixed width. Okay, and this width is this particular variable self width. Okay, and you are also given some books to you, so array of books. Okay, a book is having two things. One is its width, or how much space it will be taking. So what you are doing is you are taking the book in this particular fashion. Okay, okay, so this will be your book placed here. So this is the width of the book, this particular section. And this book will be having some height also. Okay, so for each of the books you are given these two things. Okay, the width and the height. So you will be placing your books in this fashion into the shelf. Okay, and these shelves will be having maximum width or total width of shelf width. Okay, till now I hope we are clear. And then it is saying that we choose some books to place on the shelves such that the sum of their thickness is less than or equal to shelf width. Okay, so the number of books that you will be placing, let's say you are placing some books here, so their total width or the sum of this width should be less than or equal to this shelf width. Okay, so it is very well understood even by the description till here also, that you will be able to place only the amount of the books if their width is not, total width is not exceeding this self width. Otherwise you will not be having space in the current shelf, or you have to go to some other shelf to place those books. Okay, so then build another shelf if you have exhausted your shelf width, or place your books at another shelf, okay, of the bookcase, so that the total height of the bookcase has increased. Okay, so what you are doing is initially you are having only let's say one shelf. Okay, and you place some books. Okay, so let's say these are the books that we are placing. So let's say they are of different sizes. Okay, and let's say these were the books, and let's say the book, okay, I think this must have overlapped. Let's take it to another slide. Okay, So let's say we are placing the books like this, and the shelf width is only up till here. Okay. uh, we cannot erase this for let's imagine that the shelf is only till here. Let's change the color here. So this is the shelf width. Okay, so you have to start with a new shelf here. Okay, because you have already exhausted the width. Your width was only up till here only. Okay, so you have to place a new shelf for sure, and the height of that shelf from the current shelf will be the height of the book which is having maximum height on the current shelf, this particular book. Okay, so let's say this is extending up till here actually. Okay, so this height will be the height of the maximum height book on the current shelf, and this will be the new shelf that we will be building. So new shelf. So this was some previous shelf that we were placing books on. We have already exhausted its width, so we are building a new shelf in the bookshelf, and its height will be the height which is equal to the maximum height of the book in the current shelf. Okay, so this is what we are doing here. Okay, so height of new shelf. Okay, so I hope till now it's clear to you and it makes sense. So then we repeat this process until there are no books to place. Okay, and note at that at each step, this is really important, uh, of the above process, the order of the books we place will be the same as the given sequence of the books. So what it is saying here is, so you can see in this illustration, let's copy it, and let's place it here. As you must have been able to see this, let's shrink it down a little bit. Yeah, I think it should be fitting fine now. So what I'm trying to say is, you are given some seven books. Okay, seven entries, 1 2 3 4 5 6 and then 7. Okay, and let's mark the indices also. 0 1 2 3 4 5 and 6. From 0 to 6, since it's a zero based indexing, therefore 7 books. Okay, so as you can see, you are just segmenting the array, which segment you have to place on the first shelf, which segment you will be placing on the second shelf, and which segment you will be placing on the third shelf. Okay, I hope it makes sense to you. So this was the first shelf, and after that this was the second shelf. Okay, this much, and rest of it was the third shelf. And since these are the indices only, so their corresponding book numbers will be somewhat different, a little adjusted here of one greater than the index. So the book number 4 5 6, and this one will be 7. Okay, so this is 1, and this is 2, and this is 3. Okay, I hope it makes sense. We have to just do kind of partition only. Okay, so and those partitions that you will be doing should be such that you have to return the total height of the this entire structure, or this height we are talking about, should be minimum. Okay, so total height should be minimum possible. Okay, so I hope the problem statement is clear to you. The whole thing just boiled down to placing the partitions smartly so that the total height of the structure remains minimum. Okay, and if you place these partitions smartly, then the height of the total structure can be minimized. So this is the whole thing that we are being asked to do, and we have to return this total mini height. Okay, minimum possible total height we have to return. So till now I hope it's clear to you. Then moving further, let's have a quick look at the constraints also before thinking of an approach. So according to the constraints, the length of the books will be of order 1000, and the thickness and the shelf width will be of order 1000 again of each book, uh, and the height will be of order 1000 again. Okay, so everything is of order 1000. So let's try to think of an approach. So basically, if we are seeing this as a partition problem of placing partitions optimally so that the total height of the structure can be minimized. So what we can do here is basically at each index you are having two choices. What index I am talking about? The index in a way, the this books array that you will be given to you. Okay, index of the books array. Okay, while you are traversing this books array from left to right direction. Okay, let's draw it up here. Okay, while you will be traversing this books array in left to right direction, at each per index you will be having a choice. You can place the book at current index, in the current shelf that we are using. If we have sufficient space left, if we have sufficient width, or you can say space left. Okay, the first choice will be this. The second choice can be place this book on a new shelf. And please try to understand and keep this in mind that the total width of the books placed should be less than or equal to some of their thickness should be less than or equal to this. Less than is important. It should never be it is never expected from you that you have to place consume all the space in the bookshelf. Okay, the current shelf. So that's why you can place this book on a new shelf also. Place this book on a new shelf uh, by creating it, by creating a newer one. Okay, okay, and in that way the height of the structure will also increase. So we will talk about that a little down the line. But I think now it is clear to you. You are essentially having two choices for each of the index or each of the books that you are visiting from left to right direction. Either you can place this book in the current shelf if that you are using, that if you are having sufficient space there, and in terms of width obviously, and you can take the second choice. You can build a new shelf, and as we have already talked about what will be the height of that new shelf, it will be the height of the maximum book in the current shelf. Okay, maximum height book in the current shelf. So you can build a new shelf and place your book there. Okay, so these two choices you will be having. Okay, and depending upon the choice that you make at a certain step, your rest of the choices will be affected. Okay, so this is a observation that we have to make. Depending upon the choice that you make, your rest of the choices will be affected. So let's say there are some partition sequences. There are some indices on which you place the partitions, or you start the new bookshelf. Okay, let's say you started the very new bookshelf at the 0th index, then you started at, let's say, somewhat at second index, then fifth index, and then let's say eighth, and let's say then 10th. Okay, so this is one sequence or one combination of partitions. Okay, so here this is one combination of partitions, and let's say another combination is that you are having somewhat similar combination, the second combination, combination 2, let's say we call it, and then let's say we place it at 9, and this is all. So this particular portion is matching in these two combinations. Okay, so there is a overlap of we can say sub problems there. Okay, so before going into these kind of observations of the problem structure, let's see how why brute force will not work here. Okay, for the given constraints that we are having. Okay, so the order of the size of the books, or the number of books, will be 1000, as we have already seen in the constraints. Okay, and at each of the index or each of the books we are having two choices. So 2 into 2 into 2 and up to, let's say, the books array's length was n. Okay, so up till n multiplications of 2 will be there. Okay, and you can say 2 raised to power n. Okay, order of 2 raised to power n, and as per the constraints this n is 1000. So 2 raised to power 1000 will be a very huge number if you try to go the brute force way of trying every combination out, like these combinations we have written here. Okay, placing the partitions. So that's why and there is a limit of number of operations that you can do in 1 second, and basically if you exceed this limit, usually in the online judges your solution gives time limit exceeded error. Okay, so that limit is 10 raised to power 8 operations. This is the ops limit that you will be having. So it should, your number of operations required by your solution should be well within this limit, but here you can definitely see that we are exceeding this limit. Okay, so this 2 raised to power n is greater than your limit. So here you will be getting TLE for the brute force way, time limit exceeded, and your solution will not be accepted. Okay, no AC for this solution. This was the brute force way that we were talking about. Okay, we want just a little off track to discuss the brute force way, why it will not work and why it needs some optimizations. Okay, so let's erase this brute force approach and focus upon the optimized version. Okay, for optimized version we have to make some observations, and those observations are right in front of you. You can see that there is a overlapping between two combinations. So this particular overlapping of sub problems is called overlapping sub problems property of a problem. Okay, if you are new to this kind of properties of the problems, then I will be providing links of these properties also in the description box. You can definitely check them out. So right now what I can tell you is these are overlapping sub problems. Okay, so I hope the first observation is clear to you. Now the second observation is that we have already written that down. This was the second observation. Depending upon the choice that you will be making, the rest of the choices will be affected. Okay, so this particular observation is called. So what you can observe from this particular property of the problem is that if you are having a bigger problem, let's say, let's change the color here, it's a big problem, solution is required, then you can break down this problem into smaller sub problems. Okay, solution 1 of smaller sub problem, solution 2 and solution 3, all these solutions of smaller sub problems. By sub problems I meaning that, let's say the bookshelf was only up till here, let's say the bookshelf was only up till here, so these will become sub problems in themselves. Okay, so I hope it's clear. Then you can merge them and form the solution for the bigger sub problem. So this kind of property, or the when it is being exhibited by the problem, is called optimal substructure. Let me take a new slide. So it is called optimal substructure. So when these two kind of properties are satisfied by a problem statement, then optimization technique, basically it's just optimization over brute force, can be applied, which is called dynamic programming. Okay, so what we do in dynamic programming is, as we discussed, that there will be some sub problems. Okay, so as you can see that for this much portion we will be doing extra work. Okay, recalculating the same thing again and again, so it is leading to extra work. This overlapping of sub problems is leading to extra work because we will be doing these calculations again and again. So to avoid this extra work, what we could have done, we could have just memorized this result. Okay, so let's say we memorize it. The next time you will be seeing this problem again, you will be saying that this is the answer. Okay, instead of recalculating it. Okay, result or answer, whatever you may want to call it, you will be able to recollect from your memory that okay, that was this problem is sub problem is already being encountered, we need not to do any more computations for it, we just return the result for it. Okay, as we have already memorized it, so you will be avoiding extra work. This is uh, the one part of dynamic programming. The second part is this part. Thus, from the smaller subproblem solutions, you will be building bigger subproblem solution, and at the end, you will be having the solution of the complete problem. Okay, so one way was to memorize the results for sub overlapping subproblems. Okay, and bigger solutions from smaller one. Okay, so this is in nutshell what dynamic programming is. If you are interested to find out more about it and you are new to it, I will be providing 3 links. One will be for this property optimal substructure. The second link will be you can say for dynamic programming, how and when to apply it, or what it really is. And the third one will be for this overlapping subproblem. I hope till now we are clear that we have to, why we have to apply this technique at first place, or what does this technique does. Okay, so now in order to, I think the video must have been very long till now, so in order to make the video not any longer further, let me take the code to the board and we will discuss the approach with the code itself. Okay, so let's take the code to the board. So this is the code that we have implemented to solve this particular problem, and I hope all of the code is visible to you right now, or let's decrease it in size a little bit. I think this should be manageable. Okay, so anyways, we can uh, let's break this down so that we can increase its size a little bit. Now I think it should not be overlapping and we can increase it a little further. Yeah, I think right now it should be visible to you. Okay, now without further delay, let's discuss. So what we are doing here is, as we have already talked about, so for dynamic programming there are some considerations that you have to make. First of all, that how many state variables or the variables your current state is depending upon. State is where you are at in the recursion, or you can say while you are traversing. If you are at the current state is what basically, what is the state here? State here is, or the variable on which your answer is depending, the index you that you are at currently. Okay, so the state is index you are at currently. So this is one state variable on which your state depends. And what are other state variables? So here the only determining factor is of your current state or the current position in the computations where you are at is the index where you are at. Okay, so there is only one state variable. Okay, so one state variable, which is uh, by the way index. So we will be requiring 1D dynamic programming or one dimensional dynamic programming. This is how you will find out how many dimensions will be there in your dynamic programming. So there will be one dimension. Okay, now we are clear about it. So the second thing that you must observe is, let's take a new slide here before going to the code, that how your uh, current state will be depending upon the previous states. Or if you are at a certain state, let's say this is your current state. Okay, how could you have ended upon this state? How could you have ended up on this state? So basically we are thinking backwards, like what actions or what steps we took in past that lead us to the current state. Okay, so we are trying to find the links to the previous states. Let's change the color here. So we are trying to find the previous states. So these will be the previous states that could have led to this previous states. Okay, so previous states are nothing but, if you are, what was the partition basically we are talking about. If let's say we have there is a array and you are at particular at this index. Okay, and this is your current state. Okay, so the partition for the that would have led to this particular one would have been here, or it could have been here, or it could have been here also, provided the fact that these partitions and this, if you are trying to include the current book in the current shelf that you are using, then it will be, these previous states will be restricted by the shelf width. Basically a person is standing here and trying to see the history of things which led to your current position. Okay, so he is exploring down the line, but he can go up till the shelf width, because that is the maximum allowed previous state uh, distance from the current state, in a way we can say that. Okay, so I hope till now it's clear. So these are your previous states, and each entry in this, we will be using a structure to store the memorization of the results. That will be this structure, self height till now. Okay, so till a particular index, what is your self height? Okay, then you will be adding on top of that height. Okay, so let's say height here was x. Okay, then you add this book, let's say, to this self. So this height will either be remaining the same depending upon whether this book is the largest book in the current shelf that you are adding, or it is the smaller than the largest one. Okay, so I hope it's clear to you. Shelf height till a particular index now is a index. Okay, so this is the structure that we are using to store the previous states results in order to avoid extra work. Okay, so I hope the logic is also clear to you, which states we are talking about and how the contribution will be carrying to the current state. Okay, so I hope the state transitions is also clear, but if it's not clear, it will be clear in the implementation part. So we are initially filling this self height till now structure, or 1D DP. This is the dynamic programming table, you can say, for the memorization structure. Okay, to avoid extra work and build a larger solution from smaller ones. Okay, and we will be seeing in a minute how larger solution is being built by the smaller ones. This thing of making larger solutions from the smaller ones is state transitions, how your states will be transitioning, okay, from previous state to the current state. So the state here is, as I already talked about, is index of the books in the book in the shelf. Okay, and then you will be considering each of the index in this particular array. Basically we have filled this array with maximum integer value to represent that since we have to get the minimum height, so we have taken such a value that is not within the heights of the height range of the books. Okay, so that's why maximum integer value we have taken. And uh, we are starting our indexing from the first index, not from the zeroth index. From the zeroth index, it is representing that there is no book placed, so the height of the shelf is right now is 0, no book placed. Okay, so that's why it is storing 0. I hope it makes sense to you. Then proceeding further, the current state or the indices will be starting from the first one, so that's why we have taken this length plus 1. Okay, to account for the situation when no book is placed as of now. Okay, so then you will be proceeding to the all the current states, which are the indices, by the way. And so these are the two choices that you are having at each state: the choice of placing the partition here and placing this book on a new shelf. This was the first choice or the second choice, depending upon what numbering you give them. Okay, and the second choice was this one, choice of placing the book in the current shelf and not starting a new shelf with this book. Okay, so for the first choice, we will be wanting to have the contributions of the previous state. The previous states are these states we are talking about. Okay, so let's say this is the book that is being placed in the current shelf. So what was the last book that was placed in the previous shelf? So this will be this book. Okay, the very adjacent book to it. So that's why in that kind of situation, your previous state contribution will be just one previous book. Okay, just one previous state. Okay, and you will add the current book's height to the previous state's contribution. Okay, and this will be your structure's height till now, till this particular index. Okay, and now let's explore the second choice that we are having. The second choice is, and before exploring this second choice, we will see what is the width consumed till now. If you are placing a book, then your width consumed till now will be the width of this book. Okay, it will be initialized with this particular value, width consumed, width of the self consumed. Okay, and the maximum height book. Okay, uh, let's initialize it with the current book itself. Okay, and then we are exploring the previous state contributions. Okay, so what we are doing here is, as we already talked about, we are constrained with this shelf width. If your consumed width is greater when adding this previous state book, when considering this one, let's say you are here and your shelf width was, let's say, 1 only, and this book was also having a width of 1, so you cannot consider previous state contributions here. So if that is kind of scenario, you will break the loop here and you will not consider any thing further, or any previous state contributions for that matter. Okay, and then you will increase your if that is not happening, then you can place your book in the or take contributions from the previous states, and you will increase the width consumed. Okay, so width consumed will be increased by width of the current book. Okay, and these previous states are starting from, as we already talked about, that we will be starting from here on the just one previous book and going up till the self width constrict us, or we reach the very last index, which is the first index, since we are taking 0th index as indication of no book being placed. Okay, so that explains the ranges. Okay, so this range is explained, and then we will be seeing what is the maximum height book till this partition, this previous contribution. Okay, we will be updating that. Okay, and previous state contribution will be calculated, so we will see what is the contribution of the previous state. Or if we would have placed the partition, let's say you are having this stack of books, what will be your previous state contribution? The book, or the part the index which is storing the height of the structure just before this shelf. Okay, so this is what we are doing here. So just before the previous state, or the we are considering in a way that we have included books from the current state to the previous state, and what will be the partition placed at. So the bookshelf ending, it will be just one index before the current index that we are exploring as a previous state. Okay, so then you will be taking minimum of whatever it's present in your current state. Okay, and previous state contribution plus maximum height book. Okay, so you will take minimum of this, as we have to minimize the total height of the book structure. Okay, and then you will be simply returning your self height till the very last book is placed. Okay, so this is the whole approach, and this is the implementation also. And if we talk about the complexities, so that complexity wise it will be time complexity wise, since we are using a nested loop, it is running for the length, and the second loop is also running for order of n, so you can say order of n square will be the time complexity. Okay, and space complexity wise, since we are using a linear array to store, so in that case the space complexity is only order of n, where n is the number of books. Okay, I hope it's clear, and I know the video was a little longer, but it was necessary for me to give you the background behind this approach, and way of thinking towards applying dynamic programming to a particular problem. And I really hope this solution video added some value to your journey of honing your DSA skills. If you are having some doubts or any queries in general, then you can ask them in the comment section. Until next time, keep practicing more and more problems, and I will see you in the next video. Thank you for watching.